Hello, everyone. Let me welcome you at the second session of our symposium, Leśniewski, Logic and Ontology, organized because of the World Logic Day. And our first speaker in the second session is Professor Srećko Kovać from Institute of Philosophy from Zagreb, Croatia. The title of his paper is Interplay of Logic and Ontology in the Emergence of Modern Logic, Some Aspects of the Development.
Thank you very much. I hope you can see the screen if everything is okay.
Yeah, it's great. It's great. We can see.
Okay, thank you. So the topic I would like to present is the interplay of logic and ontology in the emergence of modern science. So just some aspects of this development. It seems that conventional view of the beginning of modern logic and analytic philosophy is such that modern logic and analytic philosophy begin with Frege and Russell, or especially when we are speaking of logic, maybe with Boole in the middle of the 19th century. However, as investigations in recent decades confirm, there are deeper roots with ramified development, and some of them neglected in the course of history, although they are, as it seems, significant contributions to the context, perhaps with latent in history undeveloped potential. I would like to trace back the roots of modern logic and of its interplay with ontology to Leibniz and Kant, and follow some lines of development through Herbert Bolzano, their successors, and algebraic logic, which finally contributed to the context of Leśniewski's work. Here is a scheme of the considered fragment of the historical development. I would like to focus, or sometimes just to mention, for example, Leibniz and Kant, Bolzano, Herbert, Robert Zimmermann, Naj Twardowski with algebraic logic, and Leśniewski. So to start, for Leibniz, the principle of non-contradiction is the principle of necessary and eternal rational truth, comprised for Leibniz in the divine intellect. Internal truths involve concepts, essences as real possibilities, and have logical and ontological significance. On the other hand, the principle of sufficient reason is, for Leibniz, causal principles related to truths and facts. Just to have time under control. On the other hand, Kant clearly demarcated logic with respect to ontology. He separated logical from real predicates, as is well known. Existence is, for example, not for him a real predicate. Then the so-called reflection concepts like identity, difference, accordance, opposition are also logical but not real concepts. In Kant, a metalogical term can be recognized, as it seems. Ontology is for him dissolved in what he calls transcendental philosophy, or as we may say, metalogic. So metalogic is almost the literal translation in Greek of the term transcendental logic. And in Kant, metaphysics is confined to moral religious philosophy. So to mention three aspects. First, deduction of all basic logical forms from transcendental unity of apperception can be reconstructed from fragments in Kant's Kant's work. This concept, transcendental unity of apperception, is simply possible logical awareness which follows our thoughts and intuitions. Then second aspect, what Kant calls metaphysical or subjective deduction of categories. Logical forms are applicable to our sensible intuition, and in this application, they yield what he calls categories. And third, transcendental, what Kant calls transcendental or objective deduction categories. Each perception is subsumed under some category, and thus to formal logic. We can recognize in Kant a concept of an overall model, having as the first element thinking subject in the sense of the unity of all thoughts, domain of the model. Then second member, world, in a sense of the totality of each of the relations between states of affairs, say temporal relations, space relations, or causal relation, and so on. And the third element, God, in the sense of the unity of all real predicates, from which things become their determinations. Let us know that Kant's logical forms are common stuff in logical textbooks of the 19th century and later. That, for example, Hilbert referred to Kant when introducing symbolic operations for sensible verification of reasoning in a formal system. The Frege praised Kant for the concept of analytic judgment, and that Gödel praised Kant for anticipation of incompleteness of mathematics, although in Kant it was related to geometry instead of correctly to arithmetic. And now I would like to follow the development characterized by abandoning abstract or transcendental subject and against psychologism. First, Herbart, who proposes normative, as we can say, ideal metalogic. It is content focused, that is focused on what is taught, focused on concept. And content is, for Herbart, neither a real object nor an actual act of thinking. Content is understood in Herbart, content of a concept, as a sum of the nodes in this concept, and the extension of a concept is for him collection of concepts with this concept, say A, as a node. And then in a judgment, concepts, that is the content, are assumed as subject or connected with what is assumed as predicate. In their interrelations, concepts are posited or negated. In German, it is setzen, aufheben of concepts. And in a result, we have positive or negative propositions. The judgment as a whole is a positive or negative decision, according to Herbart, about the question on the connection between the subject and the predicate. And let us also remark that mathematical presentation of logical forms is used later in Herbart school. In Bolzano, as is well known, objective, self-subsistent, but non-ontological metalogic, as we can call it, is present. Objective propositions, truths, representations, so propositions in themselves, are for him independent subject matter and content of our knowledge and thought. And as Bolzano expresses himself, there are propositions or ideas and so on, but not in ontological sense, just as non-actual, non-existent, non-being something. So a clear distinction from ontology. Models can be said to are introduced instead of ontology by Bolzano's famous method of variations. derivability and inference are, according to Bolzano, based on model theoretical variations on constituent parts, ideas of propositions. Now, continuing on Bolzano's approach, we have Robert von Zimmermann in his first phase. Later, he was influenced by Herbert and Herbert's school. Zimmermann's approach in logic is largely set-theoretically extensional, combined with intuitively extensional and intentional approach. For example, the influence of Bolzano is evident in concepts such as objective proposition, objective concept, form of categorical proposition is A has B, as in Bolzano. There are in Zimmermann concepts, Bolzano's concept, compatibility, derivability. There is a method of variation, and so on. For example, Zimmermann explains inference by Bolzano's derivability, and individual forms of inference he usually explains extensionally by a set theoretical analysis of the relationship of the extensions involved, as well as by Euler diagrams, as in the following example. We have not enough time to analyze it completely, but so the explanation of this inference, actually 3 inferences, is quite completely in set theoretical terms, as if in some contemporary logic textbook. So here is another example from this first edition of Zimmermann's logic textbook. However, in the 1860 and 1867 editions of his textbook, Zimmermann adopted Herbartian content-focused approach. Now, the general formula for the content of a composed concept is for him f, so it is a function, value of a function, f of ABC and so on, where f is the form of the combination and ABC are the material of the content. And by the notation as presented here on the slide, this second presented formula, Zimmermann expresses that the content f of AB is one and the same in the contents f of AB, but also f of ABC and so on, containing beside A, B, also other nodes, D, E, F, G, H, and so on. For Herbart, the extension of a concept is conceptualized. For Zimmermann, extension of a concept is conceptualized as in Herbart. The extension of a concept with the content f of B, f of A, B, consists of the concepts with the contents where beside A, B, there are also C or D, E or F, G, H, and so on. And finally, concepts are posited or excluded regarding their connectability with one another, or each time, or sometimes. Judgment is decision about the question of some connection between S and P, as in Herbart, and so syllogism consists of a special arrangement of positing and excluding concepts leading to the decision on the connectability of S and P. The general form, as we have it in Zimmermann and Herbart, f of ABC and so on, of a content, of a concept content, paved the way to any formally mathematically expressible interdependency of nodes. The Herbartian distinction between the decision and positing of concepts prepared formal distinguishing between assertion and proposition. And in particular, occasional use of algebraic expressions, general positive stance to the use of mathematical methods in logic, also in psychology, for example, as well as recognition of an mediatory ontological rule of mathematics, facilitated introduction of mathematical logic and adoption of algebraic methods in logic, as we see it in Zimmermann's student Albino Nagy. Zimmermann's ideas, as can be seen, are present in Twardowski. For example, for content-object distinction, Twardowski refers to Bolzano. Referring to Twardowski refers to Bolzano and to Zimmermann and Carey. Referring to Zimmermann, Twardowski says that content-object distinction should be expressed in the following way, as in Zimmermann. Content, first, content is what is represented in a representation, while object is what is represented by means of a representation. And on the other hand, extension of a concept is objects referred to by a concept. And the second example of the reference to Zimmermann in Twardowski is when Twardowski expresses his understanding of object by means of the formula in this line at the bottom of the slide. So G, object G, is the value of some function f for T1 to Tn, which are parts of this object. For Frege, the starting point is not concept, but judgment. Thus, content of a judgment comprises not just sense, but also truth value. And extension of a concept for Frege, as is known, is what he calls course of values of a concept function for objects. And so in ontology, for Frege, we have concepts which are unsaturated, and the rest of ontology are objects. Leśniewski was questioning these distinctions, but adopting a whole part approach. For example, although Leśniewski held Frege in great esteem, he critically claims not to understand what does Frege mean with the extension of a concept, or with that the extension attaches to the concept itself and to it alone. Now to the question how algebra comes into the story. Leśniewski says, when speaking about his logical system, when he is speaking of a protothetic, he says that it corresponds in content, although very roughly, to the theory known in the science as calculus of equivalent statements. So to Aussagenkalkül, and he refers to Schroeder. He also mentions other logical theories. And for his ontology, Leśniewski says that it forms a certain kind of modernized traditional logic in which so ontology in content and power most nearly approaches the Schroeder-Klassenkalkül, considered as including the theory of individuals. Frege criticized Schroeder, for example, in the following aspect: for not distinguishing membership from subset relation. He says that this distinction is blurred in Schroeder. Schroeder does not distinguish, according to Frege, individual from class, and Schroeder is, according to Frege, inconsistent about the question whether there is empty class and whether element D is the same as the singleton D. Also, as Frege mentions, Schroeder's basic concept of Gebiet, domain, is not clear. Regarding these distinctions, Leśniewski was closer to Schroeder than to Frege. Now, within Vienna group of philosophers and logicians, algebraic logic was dealt with by Albino Nagy, who studied with Zimmermann and Brentano together with Twardowski. He brought more clarity to the above questions, later mentioned by Frege, and entered deeply into the foundations of logic and ontology. So let us see how does it look in Nagy. The primitive concepts, or one primitive concept Nagy starts with, is logical quantity, or the thinkable. It is described by three postulates on three primitive relations. So, first relation is that with a quantity A, another quantity B is taught. This is inclusion relation. Then, secondly, with a quantity A, a part of quantity B is taught. This is partial exclusion, involving partition of B. And the third relation is that with a quantity A, quantity B is not thought. So it is total exclusion. Now, logical applying algebraic operations to these primitive relations, Nagy is able to define logical entity or element or individual by a limit identity with the product of logical quantities AI. So AI from 1 to n with growing n. And this is based on the proof that it is always possible to find an plus 1 such that the product of AIs from 1 to n minus the product of AIs from 1 to n plus 1 is always greater than 0. Nagy stresses that his definition came prior to Schroeder's different definition of individual as a special case of class. In Schroeder's definition, it is simply expressed that individual cannot intersect both with X and Y if X and Y have empty intersection. Further, Nagy clearly distinguishes element or entity and class. The same operations, sum product, are applicable as for classes, but with different results. So the sum of elements EK from 1 to n is a class, except for the case when this EK is always one and the same element, and so this sum is then an element, not a class. On the other hand, the sum of classes is always a class. Thus, logical quantities, so it is this primitive concept, are not only classes but also individuals. A sum of different entities is a logical class in a narrow sense. For Nagy, plurality of entities in clear distinction to elements. Otherwise, product of EKs from 1 to n is empty class, except in case that this EK is always one and the same element, and then this product is precisely this element E. On the other hand, the product of classes is always a class, possibly 0 in case of disjoint classes. I would like to skip this slide. Nagy also speaks of a class in the strict sense, which is generated from an element with k variable places between certain limits. And here is example with k equals 1, one variable place. So from A1 to AN, but with variable A, k from negative infinity to positive infinity. Possible origins are of course, in Bolzano's method of variation. Nudge thinks that proceeding to higher and higher degrees of classes by means of this method of variation, we arrive at the whole domain of the thinkable and accomplish in this way his intended proof of the logical ontological completeness of the algebra of classes. And individuals are the basis of the logical ontological construction, but in continuity with classes. Another algebraic question dealt with by Nudge is the so-called Gibbons-Clifford problem. This is an approach with continuing partial extension of logic and ontology by new and new logical, ontological types of logical quantities. It is the question how many and which are the types unchangeable under mutual substitutions of literals and representants of types obtained by mutual substitution of literals of propositions or Boolean propositional functions characterized by TMN, M for the number of constituents of a complete disjunctive normal form, and N for number of elements, letters, atoms. Arkart, in his paper, says that with the appearance of the Frege-Peano-Russell's approach to logic, this Gibbons-Clifford's problem was largely forgotten, but the interest in it was reviewed later, since 1930s, in electroengineering and computer science. However, relating to the problem of types, of concepts and propositions, Nudge and others are mentioned, for example, by Gödel and later by Bernays. Nudge gives, from his side, a procedure for the solution of some part of the problem, which, for example, Gödel recorded for himself in his notes, and the general solution was given by Polya in the 1930s. Let us briefly illustrate types by the example with two elements. So M disjuncts and two atoms. For example, if we take a look just at the types Roman 3 and Roman 4, in type Roman 3, we have the difference between two disjuncts only in one literal. So it is said the distance structure of this type is 1. In contradistinction to the type Roman 4, where we have difference in both literals, difference between disjuncts. So it is said distance structure of this type is 2. So this distance structure further gets more and more complicated. For example, type 4, we have three pairs of distances, and in type 6, we have 4 triples of pairs. Let us just notion that the number of types grows very rapidly. For N3, 3 atoms, there is 22 types, and so on. For example, for 5 atoms, the number of types is already over 1 million. Types can be presented in tableau and correspondingly in a sequent format. For example, this type 3 with distance structure 1 can be presented by this branching format of a tableau, and it could be presented by corresponding pairs of initial sequence in these two presented sequent calculus derivations. So pairs of initial sequence are reducible to the same type by negation rules. And as can be seen, we have in this initial sequence non-empty identity of antecedents or succeedents, and thus it is possible to apply branching rules, left disjunction and right conjunction, in such cases. For type 4, we have also here a tableau format with these two branchings and one corresponding pair, which corresponds to the left branching above. So a corresponding pair of initial sequence. Here, in distinction to type 3, we have no identity or, so to say, formally empty identity of antecedents or succeedents, and accordingly, only empty application of the branching rules of the sequence calculus are possible. Now, by adding such initial sequence, non-axiomatic initial sequence to sequence calculus, we have, of course, the question of cut admissibility, whether it is valid when we extend calculus in such a way. So some propositions for cut admissibility are provable. This is one example. We can start from an existing cut admissibility proof, as is the proof by Andrzej Jędrzejczak. And for example, we can extend the base of induction by considering premises which are postulates. So postulates this non-axiomatic initial sequence of this or that type that contain parametric cut formulas. And if the left premise is a postulate, as can be seen in this example, the conclusion is then also a postulate of the same shape. And similarly, if the right premise is a postulate. Then in this example concerning sequence type 4, we have in application of cut axiom as a result, and so we can simply eliminate this application of cut. But for some cases, we need to redefine the set of initial sequence of various types by including some sequence containing the top or bottom in appropriate places, which result from the application of branching rules to postulates. This idea is actually similar to the idea of Piazza and Tesi, which use cut closure to enrich initial sequence added to sequence calculus. So here is one example. If we wish to eliminate cut in this case, we, as can be seen, arrive at the conclusion which has top, that is B or non-B, in the antecedent of the conclusion. And we are, by this new definition, we can simply introduce into initial sequence this conclusion, but with deleted B or non-B. And in this way, eliminate the application of cut. So here is another example generalized, where we have in the succeedent, in the conclusion, AK and non-AK, and we can simply delete it from the conclusion, and the rest of the conclusion we can then include in the initial sequence of the calculus. And finally, let us come to some examples of propositional or class types in ontology. First example is Leibniz ontology proof, its first part, which proves the possibility of the most perfect being using only types 1n. So one disjunct and any n of atoms for the finite case. And perfect properties are, for Leibniz, simple, taken to be simple, positive, absolute, and so non-analyzable and non-definable, and thus compatible. In this way, Leibniz was able to give a methodological proof that it is possible that there is some entity which possesses all these properties A1 to AN. Second example of types in ontology is can be found in Kant. For example, his regulative idea of world. There we have the progress to new and new states of affairs in space and time, or in a series of causes. Also, second example, regulative idea of God, where we examine new and new predicates for the full determination of a thing. Third example is Gödel's ontological proof with what he calls attributive interpretation. There, all types for any number of disjuncts M and any number of atoms N are included, but with their representants which contain a purely positive disjunct. So one disjunct is simply atoms, conjunction of atoms A1 to AN. A possibility proof can be then, of course, similar to that given by Leibniz. Otherwise, it can be a proof in object logic, in second order modal logic with third order property of positivity, as it is presented in Gödel's ontological proof, because each representative of a type can be transformed by substitution of literals into a representant with a purely positive disjunct. And some of the recent examples is Logic of Change by Professor Srećko, which considers change in a developing world through stages with increasing number of atoms. So, thank you very much.
Thank you very much. And it seems that we have time for one question or comment. Okay. Professor Świętorzecka.
Hello. Yes, maybe. Hello. Hello, Srećko. Nice to meet you.
Yes, hello, hello.
Thank you for this excellent talk. It is nice to see you and to hear you. Thank you that you told me that I have some connection with Navi. May I ask you really what is the connection? I didn't understand why my logic is somehow, this idea is connected with these types.
So it is quite simply, as I recall rightly, you have simply world which develops by adding new and new atoms. Am I right?
Yes, this is true. Yes, this is true.
So it is, and it is simply this by adding new and new atoms. It is this m. So we have types m, n, and this n is the number of atoms. And so this type grows, so to say, by increasing this index n. And so what in your ontology of change, you have, so world develops through two, let us say, so higher and higher types with greater and greater n. And of course,
Yeah.
it depends how each of these stages is modeled. We have this or that number of disjuncts. So it is this upper index m. So this development of a world is can be seen as a development to new and new or richer and richer types. So,
Okay, thank you.
so it is how I have understood.
I will think about it. Thank you very much. Thank you.
Thank you so much. Okay, so thanks once again for drawing this beautiful picture of connections of ideas between Kant, the 19th century philosophers, and Professor Świętorzecka. Thanks once more. Yes, thanks, Professor Kovać. Yes, thank you very much.
Thank you too. Thank you.
Yeah, and now it's my pleasure to introduce our next speaker, Professor. Zuzanna, do you want to add something? No, I think sometimes we are mixing the raising hands with clapping hands, so it's confusing in Zoom. Okay. Okay, now our next speaker is Professor Vihren Bouzov from St. Cyril and St. Methodius University of Veliko, Tarnovo, from Bulgaria. Hello, dear Professor. It's so nice that you joined us again. You also presented your paper during our last symposium on Kazimierz Ajdukiewicz. And today, Professor Bouzov will present the paper on eternal truths, truth conditions, and the logical principle of excluded middle.
Thank you very much. I would like to say at the beginning that it is a great honor for me to participate in this seminar and in our research activities of Warsaw Research Center. I remember that 30 years ago, at the beginning of my academic career, I started with 4 months research stay with stipendium of Casa Mianowskiego Foundation in Warsaw under the supervision of Professor Ryszard Wojcicki. After that, 4 years after, I have another research stay in Krakow on with stipendium of King Jadwiga Foundation with study of Polish analytical tradition in philosophy of law. I am teaching logic and philosophy of law. So it is a good option to continue and to continue my cooperation with Polish philosophers and logicians. Now I will start with my presentation. So it is the content. I will start with some consideration on logical laws and logical principles. I turn to the papers of Leśniewski and Kotarbiński from 1913, because of my interest in the possibilities of logic to provide means for thematizing and the development of things and in an ontological context and on future events. I have participated in Bulgaria here in some discussions about possibilities of logic to analyze and represent the process of creativity and some dialectical aspects. In my course of logic for philosophy and for law students, I teach about many valued logics and the philosophical arguments of Łukasz to rethink the foundation of logic. I agree with him that sentences that affirm contingent future events today are neither true nor false. I suppose that Leśniewski's arguments can be strengthened and justified by reference to truth-meaning relations and to semantics that can grasp sentence meanings and thoughts expressed by them, such as the possible word semantics. In my philosophical views, I accept realism and would like to reject relativism on the issue of truth, and I oppose to categorical mixing of abstract entities such as thoughts, meanings, propositions, principles, and talking about real object. Logical laws express basic characteristics of human thinking: validity, definiteness, consistency, adequacy. They are not characteristic of the arrangement of thoughts, insofar as the arrangement of thoughts reflects the dependencies between things. They have an objective character and are laws of reality itself. The laws of logic are not only feathers on the linguistic expression of thoughts, because the structure of language corresponds to the structure of reality. Logical laws can be explicated in ontological, epistemological, linguistic terms. A logical law can be formulated simultaneously as a principle of reality, a law of thought, or a norm of language. The law of excluded middle states that two contradictory propositions cannot be simultaneously false. One is true, the other is false, and there is no third in between. It is related to the principle of bivalence, which underlies classical logic and is invalid without it. Every proposition is either true or false. The idea of non-classical logical systems and arguments points to limitations in the universality of this law. It does not prove valid for every way of thinking, and in particular for statements about future events. Łukasiewicz's critical analysis shows that accepting both principles is to the affirmation of strong or ultimate determinism, and the thesis that everything is bound up in infinite causal chains. The principle of bivalence rests on the choice of a philosophical position, and its rejection entails the rejection of the absolute determinism. This type of logical determinism implies fatalism. In the article, The Problem of Existence in the Future, Kotarbinsky starts from the premise that term exist can be understood in two ways. On the one hand, it means X is available here and now. On the other, X exists leads to the judgment affirming X is true, where the judgment, the object P, in time T, and place M has the property C, affirms the objective fact that P possesses the property C. We face the problem of the existence of past and future objects only in the second understanding of existence. Kotarbinsky assumes that if the sentence is true at the moment, it will be true at every subsequent moment. This argumentation leads to the conclusion that all past objects exist in the present in the indicated sense. Past facts are divided into those that have existed since the beginning of the world and those whose existence begins at a certain past moment. The latter are the result of human creative activity. Thus, it turns out that a necessary condition for the existence of a given fact S, X, is the absence of the is its absence at the moment of creation. If there is a freedom of creativity, judgments that affirm a possible effect of a certain action in the future cannot be either true or false in the present. For example, in Bulgaria, it is an example from Bulgarian policy. After 7 unsuccessful elections, we can say in March or in June this year, Bulgaria will have a regular government. This assumption limits the applicability of the principle of excluded middle only to definite judgments. In this initial period, Kotarbinsky defended the existence of indefinite sentence, neither true nor false. Such sentences have to refer to past events caused by someone's free action. The Polish philosopher adopted the classical definition of truth from Aristotle, and in order to reconcile it with the existence of indefinite sentences, restricted the law of the excluded middle to definite ones. This led to the rejection of the belief that truth is without beginning, insofar as it did not require a revision of its eternity. He writes that the one who says correctly is the one who accepts that what has passed has not ceased to exist, but has only become non-existent. What was happened has really happened, and the one who claims that it is so, and therefore what exists says correctly. Leśniewski begins by criticizing the way in which the term existence is understood in Kotarbinsky article. He correctly notes that the proposed definition of existence excludes things from the realm of existing objects, allowing only the relation of inherence of a property of an object. The conclusion is justified that regardless of the way in which the property of existence is defined, it can be inherent to an object only on the condition that it is present. This conclusion rejects the truth of Kotarbinsky thesis that past objects exist eternally. It is a quotation: if only relation of inherence can be asserted by affirmative judgments, then of course only relation of inherence can be such objects that affirmative judgments referring to them are true. For if some object other than a relation of inherence were an object such that an affirmative judgment referring to it were true, then an object which is not a relation of inherence would be asserted by this affirmative judgment. Such a generalization and the established contradiction exclude the truth of the thesis about the eternal existence of past objects. Leśniewski accepts Kotarbinsky thesis about the eternity of truth by proposing a proof for it on the basis of the principle of contradiction. In an analogous way, he proves the conclusion about the existence of truths without beginning. These two statements can be combined into one, which asserts that truth belongs to judgments regardless of time. Thus, he denies the claim that it is possible to create some truth, or that it is possible to make a judgment that was not true become true at the same point. I could summarize that Leśniewski is quite justified in criticizing the claim that the existence of truth without beginning rejects the free creativity of man. He believes that such a thesis is not reliable, logically grounded. I suppose that additional weight can be given to this argument of Leśniewski by invoking the connection between truth and meaning. We understand a judgment when we know under what conditions it will be true, what its truth depends on. Truth conditions refer to the actual presence of the object asserted on their properties and relations. When we explain the understanding of judgments through the concept of truth conditions, we are actually explaining the concept of meaning to which the concept of understanding refers, through the concept of truth, to which the concept of truth conditions refers. Through this analysis, we also come closer to understanding the meaning of the sentence in the semantics of possible worlds. I agree with Professor Wyszyński critical remarks that if the eternity of truth is not in doubt, but equivalence of the eternity of truth and truth without beginning can be challenged by rejecting logical determinism as a type of ontological fatalism. Even if they are equivalent in a logical sense, they are not so in an intuitive aspect. The beginninglessness of truth means that it truly deprives a person of the ability to change circumstances and control their own destiny. It is unacceptable from a logical and a worldview point of view. What does it mean that truth is a property of declarative sentences? This means that truth and untruths are meanings of this sentence. They are precisely expressed by propositions as abstract entities. Understanding sentences characterizes linguistic expressions of action. The analytical tradition after Frege and Wittgenstein assumes that we always think in science, in sentences, and only through sentences do we have access to the objective content of things, to thoughts, and thinking is the comprehension of thoughts. It consists in understanding the sentences with which we articulate them. Propositional thinking is related to understanding language, the propositional language with which people communicate with each other. To understand a sentence means to know under what conditions it is true, or to know the condition for its truth. The semantics of truth conditions appears with Frege and was developed by Wittgenstein and logical empiricism. To understand a sentence means to seek an answer in its semantics of truth conditions. To understand a sentence requires not knowing whether it is true, but what its truth depends on. Leśniewski offers his own definition of truth. The starting point is the notion of symbolic function for sentences of a type A is P. He proposes as formal truth conditions for every proposition. First, a true proposition always possesses a subject which denotes something. Second, a true proposition always possesses a predicate that connotes something. Every true proposition possesses a subject which denotes something. Wyszyński rightfully says that here there is an error when we read that every proposition whose predicate connotes or represents nothing is a true proposition, because the final conclusion in this argumentation contradicts this. The symbolic function of representation rests on the fact that the object signified by the subject possesses the properties signified by the predicate. A proposition is true if and only if it has a symbolic function. Every true proposition has a signifying subject and a signified predicate. Every proposition that does not have a signified or empty subject or predicate is a false one. To establish whether a sentence is true means that we understand its meaning and the object spoken of exist directly. The object may not exist, as this does not affect the thought spoken of in the sentence. This object is important for establishing the truth of the sentence. To the thought of the sentence are the criteria for identifying the object, the mode of its presentation. The truth of the elementary sentence, if A, depends on whether the object A, however we refer to it, has the property of being if, and the thought that it expresses presupposes that the object identifiable as A, whatever it may be, has the property F. Kripke rightly objects to truth conditional semantics, drawing attention to the fact that to give the meaning of a sentence, it is not enough to indicate the truth condition that it has in the actual world, but the truth condition that it has in every possible world. Predicates do not have a literal reference, but they do have a certain relation to extra-linguistic realities. Through predicates, objects are classified. Certain objects are distinguished as being in a spatial relation to the predicates, insofar as certain properties and relations are truly stated about them through the predicates. This allows us to reformulate the truth condition of the elementary sentence. It is true when the object A is an element of the class defined by F. Unlike the intensions of predicates or concepts, which are the same for every possible world, the extensions of predicates, sets of classes, change in different possible worlds. The intension of an elementary sentence, Fa, is the proposition which is expressed by it, and the extension is its truth value. At the same time, the intension of a function is the concept it expresses, and the extension is the class of object it defines. The intension of the argument A is its meaning, and the extension is the object to which it refers. Of all these entities, only the object is something concrete, and all the others are abstract entities. The proposition is the thought expressed in the sentence. The concept and the class are also contradicts concept. The class are also abstractions from language. Thus, Kuterbinski argument unjustifiably mixes concrete object with abstract categories. The former must be present in order to make true statements about them. We have an alternative concept with which to describe the intention of A. The expressions intention of A and the sense of A are synonymous. This is a problem that was established as early as Frege, who did not have a technical term to express the sense of. Carnot speaks in the case of the intentional of the singular term of an individual concept. But this seems misleading because we are talking about concept in the intentions of predicates, and it would seem that the intentions of singular terms are a special kind of intentions of predicates, and also because in the philosophical tradition, concepts are associated with universals, not with individuals. We establish that sentences express thoughts which we understand together with truth of the sentences. Next is the thesis that the singular terms denote objects. It is about two objects of thinking: what we think, the thought expressed by the sentence, and what we think about, the object that a given singular term denotes. The intentions of expressions are functions which for certain possible worlds, possible situation or conceptual descriptions, C1, C2, and so on, give an arguments certain extensions as values of these arguments. The extension of an expression in a certain world is the value of its intension for C. Propositions are functions which give for possible worlds as arguments truth values as values of this argument. Concepts are functions which give for possible worlds as arguments classes as value of these arguments. The senses of singular terms are functions which give for possible worlds as arguments objects as value of these arguments. These arguments, together with the application of semantic analysis, lead to the restoration of the correspondence concept of truth as the relation of the sentence to reality and objects, and to the revelation of the essence of understanding as the establishment of meaning. These are the references. Thank you very much for your attention.
Thank you very much. Okay, and then we open the discussion. Are there any questions or comments to the professor's paper? Yes.
Hello, Professor Bouzov. Thank you for your presentation. I have maybe missed about the eternality of truth. That you say that the eternality of past objects hold. And now I have a question about a sentence generated by my brain, and that is, can we say that now or on all times on the earth or in the universe, can it hold to say that the capital of East Prussia is Königsberg, or capital of East Prussia was Königsberg? I can't understand that in the time East Prussia was existed. Can I say aber or too in this time, in the past time, that the capital was Königsberg?
Yes, it is the meaning of a sentence, but the object called Königsberg does not exist now. So I think the argumentation of Leśniewski is right against the Kotarbiński.
Okay.
Okay, I apologize, but I also have class this afternoon. I will leave the seminar. If you have not other questions, thank you very much and good luck for the research center or for the seminar. Thank you very much.
Thank you.
Bye.
Thank you very much, Professor Bouzov, for joining us. If there are no other comments or questions, no? Okay, so I think, yes.
If I have one short another example because the one of the participants gave an example of the Königsberg as a capital of East Prussia, and now after some historical changes, there is no such a state. But can we talk? Can we state? Can we say that as for the past events are still in present, are existing in presence? Can we say this about the last year seminar about Książkiewicz? You have participated in this seminar, and this is another example because there is no state historical changes and wars involved, and maybe we can say that this seminar exists in some way, still exists in our hearts, for example. Thank you.
Of course, this sentence that this seminar was realized last year was true, but the event does not exist now. We are in the next seminar now. I think this way of thinking is right. Okay. Thank you very much. Thank you.
Thank you once again. And
Bye.
yes,
Thank you.
Since we have 10 minutes to another talk, let's make a short break. Let's have some air in the room, and then we will introduce our next speaker.
Devoted to the question, in some way, theory how to pose questions, indeed. But firstly, I would like to state that there is a false statement in my presentation, but I won't tell which one. And okay, so why Professor Pogonowski? I did not know him personally. I know him only from conversations with other people like Cordula, and I also know him from his webpage when he put some materials from courses he taught, and indeed one of his ideas was to teach logic and mathematics through riddles. And he had even some courses based just on riddles and solving riddles. So this is why I think you would like the topic of this talk and also possibly this talk. So the origins of this work is a bachelor thesis of Maria Książkiewicz, who is here, and she translated some logical and mathematical riddles into propositional logic, and then put this translation into SAT solver and obtained solutions just by using the SAT solver. And we examined what are the possibilities of doing this, what are limits, and so on. So some riddles were taken from various books of Smulian with logical riddles, and indeed Smulian also writes in one of his books that it can be translated to propositional logic and it can be verified within just propositional logic. However, he also states that when we need to find a question, a right question in a riddle, then this requires some more work. And for example, SAT solver allows us to do this more work simply by checking all possible questions up to certain length, or simply to check that there are no more possible questions than 1,000, let's say. And we can check any of this possible question, whether it leads to a solution of our riddle. So indeed, such things are possible with the use of SAT solvers. And after that work, we decided that it would be good to prove something about riddles. So it would be good to formulate a theory of riddles. So we indeed started to think about it. And one of the most known riddle is a riddle about two twin brothers, truth teller and a liar. And we are at the crossroads. One way leads to a swamp. We don't want to go there, one to the city. And we need to ask one of this brother just one question, yes or no question. And we do not know who is truth teller and who is a liar because they are twins. So I think everyone knows what is the solution. So we can ask simply, what would your brother answer on the question, does the way on the left lead to the city? And if we obtain an answer yes, then it's a clear indication that the right way is to the city, and so on. So we wanted to formulate a general theory of such riddles and other riddles of that form. Okay, so how to make a theory? And such a theory, first we would like, but such a theory allows us to formulate a sufficiently general set of riddles, and then it should allow us to prove something about the existence of a solution, or maybe estimate complexity of a solution for a particular riddle or family of riddles. So this is what we had in mind when we started to work on that. So, but first, let us think about a more general form of a riddle, Smulian-like riddle. So let's say that we have n brothers, n agents, not just two. And because riddle is about something, so let us fix a variable r. And in one type of riddles, we just want to determine what is the value of r. This r may be, for example, the left road goes to the city. And then we know that some of the brothers of the agents are liars and some are truth tellers. So we introduced Li, which states that I is a liar, and Ti, which states that I is a truth teller. Okay, so but then we want to be able to express some questions. So we should be able to ask about any formula A. So for any formula A and for any agent I, we add a new variable which represents the answer of agent I on a question whether A is true. And this is new variable. And of course, as we add this variable, our language is enriched, is bigger. So then we need to add another such a variable for this variable, for example, because we can also ask about truth of this variable. So we add next variable. I will show it shortly. So indeed, this represents the agent I answer on a question whether A is true. And then, for example, we can ask agent 1 about truth value of R, but also we can ask agent 1 whether agent 2 is a truth teller, or we can ask agent 2 what agent 1 would answer on a question T2, however 2 is a truth teller. So indeed, here we have this variables, and here we have translations of these variables into their meaning. For example, here we ask agent 1 what agent 2 would answer on a question whether agent 1 is a truth teller. And here we ask agent 1 whether tautology is true or not. So this may be an indication whether agent 1 is truth teller or a liar, if we got that answer on this question. But we will allow also random agents. It will in a minute. And then we want to axiomatize the behavior of our agents. So we say, we add such axioms. If agent I is a truth teller, then his answers are just equivalent to the truth value of a formula about which we ask. And if it is a liar, then of course, the answer is equivalent to negation of the formula. And we also add axiom that no agent can be at the same time truth teller and a liar, because it would lead to a contradiction indeed. So in a sense, we do not need this axiom, because if this would not be true, we would have a contradiction, and we could not include. We do not need to include this indeed. So we call this theory of questions, and it is infinite because we have infinitely many variables and formulas, and for each formula we have such axiom. So the theory is infinite, and this could lead to a question whether we could, what big finite fragment of a theory we need to determine answer on some riddle. So, and if we would like our agents to be always truth tellers or liars, then we could add also axiom of that form. And in some cases, we will do this. So then we extend a theory of questions by this determinacy, somehow axioms, let me say, and we call this extension like TDQ, because each agent is determined, so each answer on each question is determined. Let us remark that if Ti and Li are false, then of course the answer of an agent I on a question A is just arbitrary. We cannot say anything about this answer. So indeed, it may be a problem if we want to determine the true value of R. Okay, so this is a language and this is a theory, and now we need to formulate what is a riddle. So let me say what kind of riddles we indeed meet in the literature. So for example, there are two brothers, truth teller and a liar. But sometimes there are harder questions, but there are three brothers, truth teller, a liar, and one of them answers just arbitrary, a random agent. And we can also imagine that we have 100 brothers and half of them truth tellers or liars, and let's say the rest is random. And what can we do in such a situation? Can we determine which road is going to the city? Okay, and so this is a description of a situation, and we need to formalize this description, and this is a description of a riddle. For example, determine the true value of R, or determine certain properties of a set of agents. For example, determine whether there are no more randoms than 1/2 or 1/3 or whatever. And so a situation, a riddle, and what is a solution? So we are allowed only to ask questions of type yes or no. So a solution we can give to a riddle is just a set of questions. And we should state something like that. If I pose all the questions from the set S, then I can answer our riddle. So I can determine, for example, the true value of R. But of course, we have no direct access to R. The only access to R that we have is through posing such questions about R, about who is truth teller, and so on. So, and from this information, we should infer, for example, the true value of R. Okay. So, okay, so this is an intuitive description what we want, and now how to formalize it. So let V, this calligraphic V, be a set of all valuations of our propositional variables in a theory TQ. And in fact, we want only such evaluations which satisfies theory TQ. And then we say that this set that C, a subset of V, is closed if for each permutation of agents, if V is in C, then for each permutation of agents, permuted V is also in C. So this property corresponds to a property of a riddle that all these brothers are twins and we cannot distinguish one from another. So indeed we cannot state whether this is a truth teller or it's his brother, which is a liar. And we say that if we have one valuation and then we just exchange who is truth teller and a liar with a permutation P, then the second valuation also should be in C. And for example, if V is a solution, then VP should be also a solution, or if V is a condition of a possible word of our riddle, then VP also should be thought as a possible situation. And yes, so this is the property we want, because this property indeed is in all these riddles. And when we fixed a set C, the set C describes the condition, the situation of our riddle. So, for example, we may state that all valuations in C are such that that there is even number of liars, or that there are only 3 random agents, and all the rest are liars or truth tellers. But we cannot say that agent 1 is a liar, because if there is a valuation in which agent 1 is a liar, and there is also one truth teller, then this one truth teller could be also 1 by this closeness property. And indeed, we formalize a riddle as a set of closed sets of valuations. These are conditions, and this is a riddle. So valuation in R, we want in a sense determine whether we have a valuation in R or not. I will show example, or maybe not yet, but there will be example. So what is a solution to such a riddle? Solution is a set of questions. So we have a set S, which is just set ask agent I about formula A, and that's all what is in this set. And what we want from this set, we will be maybe let's think about this second characterization. Let us fix F, which is a set of answers on our questions. F is evaluation of the variables on the variables in set of questions into 0, 1. So F just describes what are the answers on questions from our solution. And I say that if I have arbitrary valuation from a set C, arbitrary V, then just by if, or maybe another way, that if that I have 2 possibilities: either all valuations from C which agrees with F, with our set of answers, either they are distinct from R, or they are included in R, in our riddle. So what does it mean intuitively? If I pose all these questions and I get answers, arbitrary answers, as given by F, and I take one valuation, so these answers determine whether evaluation is outside R or inside R, simply. Here it is also stated, but in a bit other way in the first point. But if I have 2 valuations from C and they agree on all questions, then they are both in R or they are both outside R. So indeed, to determine whether evaluation is in R or not, I need only to know answers on questions from S. So thanks to this, I can state that our set S is set of questions which determines whether valuation is in R or not, whether left road is to the city or the right road. And okay, so this is how we can describe the solution for a riddle. And example, maybe it would be good to give example. So our classical riddle, we have two brothers, 1 and 2. So our set of all possible situations is the set of valuations such that this valuation satisfies our theory of determined questions because there is no random brother. And moreover, one of them is truth teller and one of them is a liar. And this can be forced by forcing that this valuation satisfies these two disjunction. So indeed, any valuation which satisfies this is a admissible valuation for our riddle. But in fact, there are only two such valuations, of course, because we have one possibility that first brother is a truth teller and second is a liar, or vice versa. So this is a complicated way to state something simple, but but at least we can see that this complicated way works in this simple case. And then our riddle is the set of these valuations for which R is 1, is true. Maybe I said 2, at least with respect to the behavior of brothers, but we have also this R, so it would be 2 times 2 indeed. So we want to determine whether valuation is from R. So the solution set is simply ask one first brother, what would you answer on the question whether R is true? And our theory, even our theory proves that the answer on this question is equivalent to R. So indeed, knowing this answer, we know R. And this is a solution, indeed. So this is a different solution than I mentioned before, because I mentioned before the solution, what your brother would answer on the question whether the left road leads to the city. And here we ask just one guy what you would answer. But if this guy is a truth teller, then this answer is just R. And if this guy is a liar, then we have a double negation here. So double negated R is equivalent to R, and we know it thanks to our theory TQ, indeed. We even don't. Okay, and the determinants indeed assure us that we ask either truth teller or a liar here. Okay, so this is example. Oh, and this is another solution, and this second solution, which I mentioned before, ask agent 1 what agent 2 would answer. This is also a good solution, but in this case, the answer on this solution is equivalent to not R. But it's no problem because still having this answer, we know what is value of R. So indeed we do not need to have a question which is just equivalent to a variable we want to determine. We can just go through negation. Okay, so this is example, and once we have this, we can also measure the complexity of a solution set. We can count the number of questions. We can count the nesting of questions, so how nested questions we ask, and we can, for example, count how many agents numbers we use in a solution set, and this is quite natural and quite useful measure. So in principle, I will use this kind of measure. How many agents I need to use in my solution set to determine the answer. And then once we formulated all that theory, all that framework, we can play with riddles and we can check what we can prove about these riddles. So let's take such a riddle. We have n twin brothers. Each of them is a truth teller or a liar, and we want to determine whether there is odd number or even number of liars. So our condition set, our possible valuations, are just all valuations which satisfies theory DQ. Okay, TQ is, of course, because theory of questions is just a basis, but we also want that all agents are determined. And then our riddle is just a set of valuations in which the number of layers is odd. So we want to such a set of questions which allows to determine this property. And what could be a solution? So one solution would be just ask each of agent whether a tautology is true. And since they are determined, we clearly know who is a liar or who is a truth teller because we know what is the value of a tautology. Another solution would be to ask just one question, and this question would be ask agent 1 what agent 2 would answer on the question, what agent 3 would answer, and so on. And then at the end, we have a tautology. So, so in this case, it's something like we take a tautology, and each time we encounter on this way a liar, we put a negation. So, so if we got an answer no on this question, then we know that there was odd number of negations on the way here. And if we and if you get an answer yes, we know that the number of negations here was even. So there are even liars, number of liars. But anyway, so here we have a big number of questions. Here we have a big nesting, but we can show, and it is quite obvious, that any solution to this riddle needs to involve all agents' numbers. Because if we missed one agent, this agent may be crucial to determine the number of liars. So there is no way to omit a number in a solution. We can form it in one question, we can take n questions, but each number has to appear. So the complexity is n indeed, upper and lower. Okay, so and then let me say about another riddle, but here we have a more complex situation because we have random agents who answer just as they want. They are consistent with these answers. So if random agent answer, let's say, not on a tautology P or not P, it answers every time not on tautology P or not P. But on the tautology Q or not Q, he can answer as he wants, of course. So let Q be a rational, and we assume that we have a fraction of random agents which is not bigger than Q. Q may be 1/2, Q may be 1/3, and so on. So Q is fixed. And let's assume that still we want to determine the value of R, which road to take. But this time we have also random agents who answers arbitrary, so it's not so easy situation. So in this case, we have indeed two important cases, namely, if we know that a proportion of random agents is less than half, then we can find a righteous way. What we should do, we should simply ask, if we have k randoms agents, we should ask 2 times k plus 1 agents about whether R is a right way. And we ask it in this nested form because we want the answers of liars to be the same as the answers of truth tellers. And this is just double negation in the case of liar, and in the case of truth teller, it is just a value of R. So it is always value of R if agent is determined. So if we ask 2 times k plus 1 agents, and we know that they are at most k randoms, when we just take a majority vote and we know which way to take. So the power of democracy. But only if there is a minority of randoms. I don't know if it is the case of our election. So what happens when we have randoms which are with proportion of 1.5 or bigger? And to determine this, we have a fact which indeed describes the exact lower bound. So assume that we have k random agents, k or less, in our set C of conditions for the riddle, and we want to determine the R, true value of R. So then any solution, if there exists one, needs to use at least 2 times k plus one question agents numbers. So how to think about it? Simply, the solution which I gave before is the optimal solution. We cannot do better. This voting system is the best what we can achieve when we deal with random agents, with k random agents, simply. So why is it so? So let us assume that the number of agents is greater than 2 times k. Okay, that's enough. If it's not the case, then it is easy to show that there is no solution at all, simply. If I cannot take another k agents which are not random. And then let us assume, towards a contradiction, that S is a solution with a complexity not greater than 2 times k. So let us assume that that my solution use just agents from 1 to 2 times k, and these are the only agent numbers which occurs in a solution. Okay, so then as it occurs, we can construct by stages 2 valuations. Valuation V0 is such that it states that R is true, and then under these valuations, first k agents are truth tellers, and the second k agents are randoms. We may have k randoms, but the answers of these random agents mimics the answers of the corresponding agents in valuation V1. And valuation V1 is such that R is false under this valuation. Agents from 1 to k are random, and agents from k plus 1 to 2k are truth tellers. So agents k plus 1 to 2k from valuations V0 mimics answers of these truth tellers from valuation V1. But on the other hand, agents from 1 to k of valuation V1 mimics answer of truth tellers of valuation from valuations V0. So on the first side, it seems like a circular definition, but it's not circular in a sense, really circular, because we can construct this valuation stage by stage. We start from questions which do not involve nesting, and then once we fixed such questions, we can go to next stage with 1 nesting, 2 nesting, and so on. And thanks to this, we can build these valuations simultaneously, simply. So indeed, even if it looks circular, we can do this without circularity. So what happens after that? First of all, we note that This second point simply. V0 and V1 fully agrees on any question, on value of variable which is a question. Because we indeed, during construction, we indeed take care simply of mimicking these answers. So agents k plus 1 to k from V0 mimics agents k plus 1 to 2k from V1, and agents 1 to k from V1 mimics agents from V0 corresponding. So indeed, any agents mimic someone from the other valuation, so there cannot be different in their answers. So indeed, we have two valuations which completely agrees on all questions, mentioning and agents from 1 to 2 times k. But these valuations, so then we have this. But this so by the property of solution, if we have that the two valuations agrees on answers on the questions from solution on questions from solution set, then V0 has to be in R if and only if V1 has to be in R, because this is the property of a solution set. But it cannot be the case because V0 thinks R is true and V1 thinks R is false, or vice versa. So S cannot be a solution set. And indeed, we see that it is impossible to find a solution which does not involve 2 times k plus 1 agents. So we have indeed a strict bound. And then, yes, okay. So what I just said this, so thank you. So let me also mention that there is a solution to this last riddle with 2 questions, but these 2 questions are so-called adaptive because we ask the second questions only after we learn the answer on a first question. So in such a case, we can deal with two riddles only, but it's another model which needs to be investigated independently, simply. And let me conclude my talk with a last statement that the first statement of this presentation is false. Thank you. Yes. Now the riddle, which statement is false and which is true. Thank you.
Thank you. Thank you very, very much. I think we have time for one comment or question. Anyone? We'll stop sharing because we can see our online participants. Okay, so the presentation was so clear and interesting that everybody are satisfied. Once again, thank you for your time, for joining us and for referring to the work of Professor Pogonowski. And now let me introduce our last speaker in this second session. Professor Rafał Gruszczyński from Nicolaus Copernicus University of Toruń. Hello, Professor.
Hello.
And his title is Regions, Spheres and Ovals, Point-Free Geometries since Leśniewski to Contemporary Times.
Okay, thank you very much. Can you hear me?
Yes, we can hear you perfectly.
Okay, that's good. And okay, let me share the presentation. Okay. Just wait a second. Okay, so is it visible, the presentation?
Yeah. Everything works perfectly.
Okay, everything works. Thank you very much. So let me begin with thanking you generously for inviting me to this event. I am very happy and I am very honored that I am able to give a talk. At the same time, I am very sorry that I couldn't come to Warsaw, but Tuesday is normally my teaching day, so I'm teaching. Actually, I start teaching in the morning. It ended in the evening, so it was just impossible to change it. But I managed to find a slot during my whole day to give this talk. Okay, so it was one more time. Thank you very much. What I would like to talk about is topic of point-free geometries, and my idea is to just give a general overview of development of this line of point-free geometries that can be rooted somewhere in Leśniewski's environment and which stretches somewhere since the beginning of the 20th century until contemporary times. So let me begin with two prominent figures from the history of geometry as such, not only point-free geometry, which are Hilbert and Pieri. And Hilbert is obviously one of the greatest mathematicians of all time. And one might say that the turning point, not only for geometry, but as some say, for the whole contemporary mathematics, is the publication of Grundlagen der Geometrie or Foundations of Geometry in 1899. It is obviously an extremely important book for geometry. Some even said, like Bell in his Development of Mathematics, that Hilbert's book inaugurated the abstract mathematics of the 20th century. So in the opening paragraph of Grundlagen, Hilbert writes something like this. Geometry, like arithmetic, requires only a few and simple principles for its logical development. These principles are called the axioms of geometry. The establishment of the axioms of geometry and the investigation of their relationships is a problem which has been treated in many excellent works of the mathematical literature since the time of Euclid. And this problem is equivalent to the logical analysis of our perception of space. So I highlighted two things to emphasize that his method is axiomatic. So this is the first highlight. And the second highlight is that it somehow relates to our experience, perceptions of space, that the ambition of geometry is somehow reveal a logical structure of our perception of space. So from the point of view of contemporary logic, we can say that the Grundlagen is a study of a certain class of multi-sorted relational structures in which are more or less of this form, where we have three disjoint domains. The first one is a non-empty set of points. The second ones and the second and third one are non-empty sets of lines and planes, respectively. Then we have incidence relations. Of course, Hilbert himself speaks about only one incidence relation, but really there are three between points and lines, in the sense that points can be located on lines, between points and surfaces, and between lines and surfaces. And finally, we have two crucial relations for the development of geometry. The first one is a ternary relation of betweenness, and the second one is a quaternary relation of equidistance or congruence, which is somehow related to our ability to compare distances in space. Yes, and so then we put specific axioms, and as you know, these axioms can be divided in the 5 groups. There is axioms of incidence, which govern this relations here. There are axioms of order, which concern particularly the betweenness part of geometry, axioms of congruence that deal with congruence, and then we have the very special axioms of parallels, the fifth Euclid axiom, probably one of the most famous axioms in mathematics. And we have two axioms of continuity, completeness, and Archimedean property. In effect, what we obtain is we obtain a system, an axiomatic system of geometry that would probably satisfy Euclid and his contemporaries. So this is Hilbert. Another important figure which will play an important role in my talk is Mario Pieri, a little bit lesser known mathematician from Italy, who published a very good monograph, La geometria elementare istituita sulle nozioni punto e sfera, which was surprisingly quickly translated to Polish in 1915 and published by Gebetner and Wolf under the title Geometria elementarna oparta na pojęciach punktu i sfery. And Mario Pieri observed and proved that basically you can construct a system of geometry reducing your basic notions to two, to the notion of point and to the notion of equidistance relation, which in the case of Pieri is not a ternary relation, is not a quaternary relation, so it is not basically a counterpart of D, but this is a ternary relation. Geometrical intuition behind this relation is quite obvious, because you can say that points P1 and P2 are equidistant from a point P if you can locate them on the sphere which is around P, basically. Yes. So in the title of his book, of his monograph, Pieri included the word sfera as a primitive notion, but really what his primitive notion is the notion of equidistance, not the notion of sphere. But simply it is easier to express some axioms as the second order axioms put on spheres, not directly on equidistance relations. And this may be the reason why he speaks about spheres in the title, but really, let me emphasize, the basic notion is a ternary notion of equidistance relation. So again, if we translated it to the language of contemporary logic, so we study structures, relational structures, where we have some domain, the set of points, and we have some ternary relation, and we choose some axioms to define lines, surfaces, incidence, betweenness, congruence in such a way as to be able to prove that what you obtain is a Euclidean geometry, so which basically is a system which is definitionally equivalent to Hilbert's system. Yes. And this can be done. So basically, what is the conclusion of this opening section of my talk is that thanks to the works of Hilbert and Pieri, geometry was a very well-developed axiomatic system at the beginning of the 20th century. Okay, but we can take a slightly different perspective on geometry as well, so on its foundations. So the standard. Let me begin with the observation that the standard ontological commitments of point-based geometries, which are done in the spirit of Hilbert and Pieri, have the following assumptions, yes? That first, basic objects are points. So points are, some pre-theoretical intuition is that these are dimensionless objects which can be seen as kind of idealizations of the perfect location in space. The space is identified with the set of all points. Figures in the system of geometry are second-order objects, subsets of the space. Some elementary relations hold among points. You know that if we have a many-sorted structure, then they will, of course, relate objects from different sorts as well. So these are the basic ontological commitments. But starting with Leśniewski, we can single out a slightly different approach. Yes. So Leśniewski, let me emphasize that he never wrote anything about geometry particularly. So what I will say in a minute is actually an attempt of a reconstruction of his views on geometry. But from his writings, you can see that these views are slightly different. Yes. So let me repeat that what follows is just an interpretation of these fragments of Leśniewski's works in which he referred to geometry. So first, there is something like an object, which is the space, which is different than the collection of all points. Yes. Moreover, we have a collection of figures, we have a collection of lines, we have a collection of planes, and as you can see, I use different symbols to denote these because these are really different collections. Yes, Leśniewski wouldn't call them sets in the Cantorian sense, as you know, because he didn't recognize existence of Cantorian sets. But basically, the collection, what we can say, for him, space was not, was no longer identified as the set of all points. And unlike in classical geometry, lines, figures, and planes, in his case, were not collections of points as such, but they were considered as kind of fusions or mereological sums of points. Yes. So if I were to summarize his approach, interpretation of his view of geometry, I would say that we have a situation in which the set is not a set of all points, that the space is not the set of all points, but the space is the fusion of all points. Space is one of figures, and every figure which is different of space is a proper part of space. And conversely, if something is a proper part of space, must be a figure. And points, lines, and surfaces are or sets of are also kinds of figures. Yes. So again, we can see that points are the ultimate building blocks of the space in the case of Leśniewski. But if we think about the opening paragraph, when I told you that even for Hilbert geometry was kind of research which is equivalent to the logical analysis of our perception of space, we can ask, can we build system of geometry which are based on more natural objects than points? Yes, in the sense maybe we can read out some logical structures from objects which are models of some natural objects from the surrounding world. And here is where, so we aim at a system of geometry which have different ontological commitments. Yes, we do not want, instead a set of figures, we do not want points, we do not want figures as sets of points. So instead of the set of figures, we have the set R, which are objects that we may call solids or regions or spatial bodies. R is ordered by the part of relation. The space is usually the largest region. Lines and planes are not elements of R, but intuitively, they can contain only three-dimensional and regular parts of space. So the intuition is basically that, or maybe as a kind of a litmus paper for building your geometry, you take the regular subsets, regular open or regular closed subsets of Euclidean spaces, either two-dimensional or three-dimensional, depends what you want to do. Yes. So putting it together, we want a system of geometry in which space is not identified with the Cantorian set of points. Space is a region, but is not an abstract figure. Again, similarly as in case of Leśniewski, every fragment, every piece, every part of space is a region which is different from space and vice versa. But points are abstracts, yes, in this sense that points are identified with classes of regions or classes of regions, and lines and surfaces are kinds of figures understand in the old sense. Yes, so we explain away lines and surfaces are abstract of even higher order. Yes, so in light of what or maybe these 4 points may be treated as a kind of a standard assumptions of point-free geometries. Yes, so the first known system of geometry, as far as I know, is the system of Tarski, who in 1929 wrote a paper, Le Fondements de la géométrie des corps, which was later translated to Foundations of the Geometry of Solids and published in Logic, Semantics, Metamathematics in the 50s. And as you can see, this is in a way a direct contribution of Leśniewski into the development of systems of point-free geometry, because in the opening paragraph of his paper, Tarski writes that some years ago, Leśniewski suggested the problem of establishing the foundations of geometry of solids, understanding by this term a system of geometry destitute of such geometrical figures as points, lines, and surfaces, and admitting as figures only solids, the intuitive correlates of open or closed regular sets of the three-dimensional Euclidean geometry. The specific character of such geometry of solids, in contrast to all point geometries, is shown in particular in the law according to which each figure contains another figure as a proper part. So let me highlight again two things. So the system is destitute of such geometrical figures as points, lines, and surfaces, but it doesn't mean that the geometry is point-free in the sense that points no longer function in the geometry. No, they are just not taken as elementary objects, as first-order objects. The idea is to explain them away as a kind of abstractions, yes? And the second emphasis is also related to what I said before, that we admit as our litmus paper for the theory is the Boolean algebra of regular open sets of three-dimensional Euclidean geometry, or some sub-algebra of this algebra, depends, yes? So Tarski axiomatizes structures of the form, relational structures of this form, such that we have a set of regions, we have a set of spheres, and we have some kind of relation, and we have a mereological structure. This is a mereological structure. Elements of R are called regions. Elements of S are called mereological spheres, or simply spheres. And the notions of region, sphere, and part of R are the only primitives, yes? And now Tarski, by a series of definitions, defines the concentricity relation, yes? What does it mean? Yes, what does it mean? Basically, how he does it. I won't be following the whole construction because it is quite complex and involves a series of various definitions, but let me show you just one construction, the construction of the notion of externally tangent spheres, yes? So what does it mean? What does it mean that A is externally tangent to B? The first thing is that A is external to B, so they do not share any part, and then for any spheres x and y, such that A is paired of both x and y, while x and y are external to B, it is the case that either x is a part of y or y is a part of x. This is quite complex definition, but the geometrical intuition is quite simple. We want to grasp this situation, yes? We want to grasp this situation. So when this situation holds, whenever we take any spheres such that A is part of it and Y is external to B. So when we take such spheres, that they must be comparable with respect to the part of relation, yes? So if I were to add, more such spheres, they would be still comparable by being part of relation, yes? Okay, so in this way, Tarski constructs the binary relation of internal tangency, external diametrical tangency, and so on and so on. And finally, he arrives at the notion of concentricity between spheres. So when he has the notion of concentricity, he can define a point as a set of concentric spheres. Yes, so a point is just a set of concentric spheres. And when he has it, he may grasp the Pieris equidistance relation. Yes. How does he do this? Okay, what does it mean? Let me denote the points as abstracts, as sets of concentric spheres by small Greek letters alpha, beta, and gamma. So what does it mean that alpha and beta are equally distant from gamma? It means that in gamma you are able to localize a sphere such that B is in a way located on its border, and alpha is in a way located on its border, yes? So we have equidistance relation in this way. And thanks to the Pieri's discovery, now we can impose Euclidean Pieri's axioms upon this structure, and we can say that the Euclidean geometry has been recaptured in point-free setting, yes? So this was the first system. Then the second system about which I would like to tell you something is the lesser known system of point-free affine geometry, which was developed by Aleksander Śniatycki, whose original name was Ciopa, who was is a quite mysterious person because I know very little about him. I know that he was a commander in the artillery units during the Second World War, and he was also a member of the group founding Nicolaus Copernicus University in Toruń just after the Second World War. And he was a student of mathematics. He was then a researcher, and he wrote a PhD thesis which was supervised by Stanisław Jaśkowski. The Polish title of this thesis was Aksiomatyka geometrii płaszczyzny z półpłaszczyzną jako terminem pierwotnym, which was translated to English and published in English in 1968 under the title of An Axiomatics of Non-Desarguean Geometry based on the half plane as the primitive notion. So what is the system of Śniatycki based on? He constructed a system of geometry which is based on the primitive notions of region, part, and half plane. And in this setting, he captures the ordered geometry. So the ordered fragment of geometry, that is this fragment of geometry, which can be formulated with two relations only, incidence and betweenness. So there is no congruence, equidistance, or any other metric notion in his system, yes? So again, from the point of view of contemporary logic or model theory, we can say that the axioms are put on the relational structures, where again, we have an non-empty set of regions. This is a part of relation, but instead of the set of spheres as a primitive notion, we have the set of half planes as a primitive notion. And he doesn't work directly in mereological structure, but in a Boolean framework. So his underlying structure is a complete Boolean lattice. This is not a big difference, but more standard for mathematics, I would say, yes. One of the assumptions is that neither 0 nor 1 are half planes. Yeah? So what he does Śniatycki. So when he have the notion of half planes, he of course puts some axioms upon it. He says that half planes are objects which are closed under Boolean complement. When you have the notion of half plane, it is quite easy to define the notion of line as a pair of complementary half planes. You can quite easily say, what does it mean that line crosses a region? What it means that line crosses a region, it means that both half plane and its complement have non-zero intersection. Easily, we can also say what it means that line separates regions X and Y. It simply means that X is a part of H and Y is a part of the complement of H, or vice versa. So we can formulate the second specific axiom of his geometry, which says that if we have regions X, Y, and Z, then there are two situations are possible, mutually exclusive situations, which means that either there is a line that crosses all three regions, or there are three lines that can separate X1 from the union of X2 and X3, X2 from the union of X1 and X3, and X3 from the union of X1 and X2. Then he proceeds with another axioms. There is an axiom which says that if you take half planes which are part of a common half plane, they must be comparable with respect to the Boolean order. So this is the axiom which is closely related to the axioms of parallels, and this actually guarantees that later on the on the point level, the Playfair axiom is a theorem of some definitional extension of Śniatycki's geometry. Then, of course, wait a second. Sorry. Oh, okay. This is the fourth axiom, and the fourth axiom is maybe a little bit cryptic when you look at the formulation, at the algebraic formulation, but basically it says something quite simple. It says that if you ever have a region, a triangular region, of course, this is infinite region, yes, but if you have something like an angle, and if you can locate this angle in the sum of two other angles like this, that this angle must be either here or here. There is no other situation. Yes? So in this setting, you can define easily the parallelity of lines, because what it means that lines are parallel, yes? It means that they have disjoint half planes. And you can define quite easily pseudo-points, as pseudo-points are just pairs of non-parallel half planes. So the geometrical idea is obvious, that the points are just like the place of intersection of lines, yes? But this is expressed in the point-free setting, and points as such are defined as equivalence relations of pseudo-points. You can strictly say what it means. The arguments are very combinatorial here. I won't be able to go into details, but this is the working in his system is particularly working with partitions of the unity of the Boolean algebra, and taking various combinatorial properties of these partitions. Yes, but the geometrical intuitions are quite obvious. So now, when you have this, you can define the notions of incidence. You can define the notion of betweenness. So let me tell you how the notion of betweenness is captured in this system. Yes. So basically, what you want to say, you want to express by means of the primitives or derived notions of Śniatycki's geometry, what it means that gamma is located between beta and alpha. Of course, the first requirement is that they must be located on the same line. Yes. But now you must somehow say that this is located in between beta and alpha. So how can you do this? You can say it in the following way. If you take any line that goes through gamma, then when you take any line that determines point alpha, then with this point you can associate four non-zero regions. This one here, this one here, this one here, and this one here. And if these 4 zero regions have non-zero join with the half plane, then you can say that this point is in an internal point of half plane. So what does it mean that gamma is located between alpha and beta? It means that there is a line going through gamma such that alpha is an internal point of this half plane and beta is an internal point of the other half plane. Yes, so that they are located on two different sides of a half plane in a way. And now working with this relation of betweenness, you can show that really the ordered fragment of geometry is provable from the axioms of Śniatycki. Yes, this is a very elegant system, and as I told you, the working is this is pretty algebraic and combinatorial work to derive all the properties. Yes. Okay, and finally, let me mention the last one system, which was developed by Giangiacomo Gerla from Salerno and by me, in which we took a more general notion of oval instead of the place of the notion of half plane. We did it because ovals, we treated ovals as point-free counterparts of open convex subsets of the plane. And it turned out that, the motivations were manifold, I would say. The first was that it was the realization of all the Whitehead's idea that you can base geometry on the notion of an oval region. But also we observed that lines and half planes can be elegantly defined by means of oval regions or point-free convex regions as lines, either lines as maximal pairs of disjoint ovals with respect to the product order on the set of regions. Half planes may be defined as those ovals whose complements are ovals too. And we can formulate very simple axioms for ovals to guarantee that we can capture the Śniatycki geometry in our setting, and this way we can slightly generalize it. We can say it as axiomatize geometry with a slightly general notion. Yes. So let me take the stock of everything of what I said now. So I started from Leśniewski, but Leśniewski himself did not formulate any system of point-free geometry. But you may say that he goaded Tarski to go in this direction, and Tarski put forward probably the first system of region-based geometry in 1929. Yes. Then Jaśkowski in 1948 proposed some certain improvements to his system, and the Tarski geometry was developed to a fully fledged theory by Andrzej Pietruszczak and me in 2007-2008. Then Jaśkowski was a supervisor of Śniatycki, who came up with a very nice systems of point-free affine geometry in the 1916. And finally, the system was generalized by me and Gian Giacomo Gerla in 2017. So you can actually trace back, as you can see, what happened now in point-free geometry back to Leśniewski, in a way, of course, in a way. So thank you very much. This is what I wanted to say. Thank you.
Thanks. Thanks very much, dear professor. It's fantastic to see that these ideas formulated in the 20s, how they work 100 years ago later. Yeah. Fantastic. And I see that Professor Simons would like to start the discussion. Yes, Peter. Yes. Peter, if you could unmute yourself.
Okay, can you hear me now?
Yes, yes.
Yeah, sorry, my unmute button is so close to the corner that it keeps closing the window. Thank you. I'm sorry I missed the first few minutes of that, but I have a couple of questions about the Tarski in particular. Tarski, as we know from various sources, was more impressed by Pieri's treatment of geometry than he was by Hilbert's, and I think he was quite right to be so. But in the short paper, even in the longer English translation, which has a bit of Mariology in it, he just simply states that, given his definition of point and so on, and sphere, that the axioms of Pieri are satisfied. Now, has anyone actually proved that?
Yes, this is a kind of a brute force method, yes, because he just assumes that his notions are good. Yes, but Brandon Bennett in
Leeds.
In Leeds.
I was his doctoral examiner back in the day.
Yeah, it's more or less at the beginning of the 20th century, 2001 maybe.
Yeah.
The axioms directly on spheres, and he showed that the axioms of Pieri can.
Okay, thank you. That's great. I will contact Brandon about that if he's still.
There is a paper region. I don't remember the title, but it has region-based geometry This is basically what you are looking for. This is the next axiom axiomatization.
Thank you very much. Brandon Bennett was a student of Tony Cohen's, and they were very interested in this sort of thing from a computational point of view.
Yeah.
The second one is, so that's very good. The second thing is, I had the idea, the thought that I might try and apply Tarski's methods to spherical geometry, to the geometry of the surface of a sphere. And I assumed then that one would take the notion of a disk as the basic entity. And what I found is that you cannot produce within spherical geometry those same definitions or analogues of those definitions, which allows Tarski to define concentricity. Because of the way in which the sphere is a closed body rather than an infinite expanse, you can't define, I think it's probably external touching in the same way that Tarski does. So my next question is, because my stamina is not what it used to be, do you know if anyone has managed to do a similar job for spherical geometry?
No, to be honest, not. I don't even know of any serious tries of doing
Mine is serious, but I'm not publishing it because it doesn't go anywhere.
Okay.
But that in a sense, that prompted me to revert to not Tarski's early solid geometry, but to his later geometry, which is based on points. And I have decided, after a long series of sleepless nights, that I'm okay with points because it's geometry, it's not the real world. So, I mean, you can do pointless geometry if you want, and it's pointless. I don't mean that literally. But I don't see anything wrong with assuming points and working things up from there and doing it the way Tarski does, which is through Mereology. So you treat a sphere as the set of the mereological sum of all points which are equally distant from a given point or are closer to it than those points. And that gives you solid spheres, and you can do other things like lines and triangles and stuff, all in Mereology. And the reason I like that is it's back to Euclid, because if you look at what Euclid says, the very first sentence of the Elements is, a point is that which has no part. Now, I mean, that's just a mereological atom. So it's obvious that if you want to do things based on points, the best way to do them is mereologically. So Tarski goes from big things down to smaller things, or he reconstructs smaller things through basically, what is it? Is it a principal filter or something like that? Whereas I would go the other way around. And I think both ways of doing it are compatible, surely.
There's nothing wrong with points, I must say. You know, I personally also like them, and I think that they were ingenious invention by the ancients.
Yeah.
This is just, I don't think that the work done by Śniatycki, for example, or by Tarski were in any way to replace, you know, the standard geometry. It was just a trial to show that you can do geometry in a different setting. Yes.
Yeah, it was an
that can be that may be applied like in qualitative spatial reasoning, for example. Yes, which played an important role at some part in artificial intelligence or knowledge representation or stuff. Okay. So motivations are not pure technical, because you do not gain anything in the sense that you cannot, for example, simplify some geometrical theorems. Yes.
Yeah.
But I think it's just do a complementary work showing that you can take a different stock of primitive concepts and develop geometry as a kind of abstract theory. Yes, something which is.
Thanks. One last question. Can you tell me how to spell the name of the second guy with the Polish name?
Śniatycki.
Śniatycki.
Yeah, Śniatycki. Yes.
I'll look him up. Thank you. Okay.
The paper is available online, so it can be.
I'll have a look at that. Thank you very much.
Thank you very much for the questions.
Okay, great.
Yeah.
I think we are
okay.
satisfied by the discussion.
Let me say 4 words. What about Carl Menger?
It is topology.
Oh, it's okay.
It is not geometry.
Okay.
Okay. He called it geometry, but any other systems I know, just let me answer these questions, like Menger, Whitehead, Nico, any other attempts to develop theories, point-free theorems of space, at most succeed in the notion of open set or closed set, but not any geometrical notions.
Great. Thank you. That's very helpful.
Okay.
Thanks once more for the talk and for the discussion.
Thank you very much.
And now I think it would be not pointless to announce the lunch break. And we will meet here in an hour at 3:30 p.m. So see you.
Thank you very much.
Oh, okay.